Hello, everyone. I am Jihye Zhang, a third-year PhD student in Princeton University. Today, I'd like to talk about superheated droplet detector response to the solar system for zero-knowledge verification. Verifying the authenticity of nuclear warheads requires gaining confidence on whether or not an object is a nuclear weapon without revealing any sensitive information. A zero-knowledge protocol, ZKP, using preloadable superheated droplet detectors. In other words, they are also called bubble detectors, has previously been proposed for this purpose. We are both extending this technique for higher spatial resolution and also developing the ZKP technique to verify fissile material in presented objects using the X-caliber neutron source, which stands for Experiment for Calibration with Uranium, which is available at the Princeton Plasma Physics Laboratory. Mission relevance. Developing and maintaining the technical means to monitor whether the terms of a nuclear arms control treaty or other international agreement are fulfilled is a critical factor in ensuring that such agreements are successful. This study could present another pathway toward a practical and robust system for the development and implementation of arms control treaties. ZKP can address one of the challenges in arms control verification, not revealing any sensitive information of nuclear weapons. So here are our experiments to distinguish fission neutrons from moderated source neutrons so that we can verify fissile material. Our neutron source, X-caliber, has two modes, collimated mode and moderated mode. You can see the cross-sectional views of each mode here. In addition to these two modes, we introduced the filtered mode, which is moderated mode with a 2-inch thick polyethylene sheet, as suggested by the collaborator from Pacific Northwest National Laboratory. So in these three modes, we placed bubble detectors at the same position and counted the number of bubbles created by high energy neutrons. This picture shows us how the bubble detectors look like after exposure. In moderated and filtered mode, even exposed for 15 times longer than collimated mode, we could easily see less bubbles in the detector. Also, filtered mode had less bubbles than moderated mode, since there is more moderation from the poly filter. With these, we counted the number of bubbles from the experiment, and I also performed MCMP6 calculations. This figure on the left is neutron spectra calculated by MCMP. This blue curve on collimated mode is dominated by 14 MeV neutrons. Orange curve on moderated mode has a peak around 500 keV, and green curve on filtered mode has a spectrum softer than moderated mode. With these neutron spectra for each mode, I convolved them with our proprietary energy dependence data. In other words, bubble detector efficiency at 20 Celsius degrees provided by Yale University to calculate the number of bubbles. The calculation was very sensitive to precise energy dependence to detector. The calculated ratio between two modes were matching with experiment within at least 1.5 sigma range. Here, two important takeaways are: first, the moderator system worked well by giving us 50 times less signal. And second, The detector also did an excellent job being largely insensitive to neutrons below 1 MeV as we expected. So far, this is what we did to confirm that our moderated system and bubble detectors are working well for the purpose of detecting fissile materials in the future. Let me change gears now. I'd like to introduce a preliminary experiment for our radiography measurements for higher spatial resolution. Here, we are interested in using 14 MeV neutrons for radiography, and it is to explore a simple preload system for ZKP. We placed the bubble detectors in transverse direction to the neutron flux, as you can see in this configuration A. If you take an example here, the bottom left, at the top of this test tube is pointing to the left, and it is half covered by stainless steel. After exposing them for about 3 minutes, we flip the detector like configuration B, and the tube is now pointing to the right. So the part previously behind the stainless steel now sees the beam directly, and the part being seeing the beam directly previously is now behind the stainless steel blocks. And then we expose them for another 3 minutes in this setting so that we can expect to get a constant bubble density across the detector in the end. We can think of configuration A like a preload for configuration B. The idea of A plus B is to get a flat signal across the detector. These pictures show response of the 3 bubble detectors at the same position, which is half covered by stainless steel. We can clearly see that the part behind stainless steel is attenuated when compared to the region looking into the neutron beam directly. Bubble density looks pretty flat when detector response is combined for configuration A and B. So it looks like our basic approach is working. The same thing, except the detector is now half covered by aluminum instead of stainless steel. Likewise, we see the contrast between aluminum resin and direct view resin after first exposure, but they look quite comparable after the second exposure with the flip. When we plotted these experiment results for stainless steel case on the top and aluminum case on the bottom, the sum of A and B shows the left and right around the boundary look very similar. I wouldn't take it seriously at the boundary at this moment because the accuracy of alignment was about 3 millimeter, which is not really good. So I performed MCMP calculation to figure out what ideal results might look like. In bulk sense, MCMP model also gave us the same results that A plus B is flat in overall. However, the peak at the boundary tells us that this preload making system is not perfect by a simple flip. Since there is too much signal at the boundary, we might need an attenuator and or more narrower slices of material near boundaries. So our next step is to make the boundary undetectable in the end with a precise preload system. In summary, we could see that the moderator system worked well by giving us 50 times less signal than the detector, and the detector also did an excellent job being largely insensitive to neutrons below 1 MeV as we expected. We made a major step forward in exploring a preload system for ZKP application, and we will work toward on refining the system for our template approach. So we will continue to use these bubble detectors in transverse direction to allow higher spatial resolution. Expected impact and MTV impact will be, this study will provide a solid scientific basis for negotiation and a viable option for implementing a zero knowledge protocol between two parties. In terms of MTV impact, close collaboration with Princeton Plasma Physics Laboratory enabled a series of neutron experiments in a safe and seamless manner. Also, with Pacific Northwest National Laboratory collaboration in place, we plan to build additional system together and conduct more runs on fissile neutron detection in spring and summer this year. And that's it for my talk. And thank you very much for listening.